And we have our next speaker also. So I would just like to introduce you both. Sanjeet sir, Dwivedi sir. Yes, yes. Yeah. He's
Good to see you.
Dr. Sanjeet Dwivedi. He is from Danfoss Drives. And sir, Mangesh Khare sir, he is from the Hella Automotive India Private Limited. So he was
Thank
having,
you.
he was discussing on the battery management system. So today we have got two persons from industry, and really it was my uh, privilege that you both agreed to be part of this FDP. So thank you very much, Mangesh sir, and
Thank you.
we'll continue.
Thanks a
And
lot.
yeah, thanks, sir. And
So,
now we'll proceed with the next session of Dr. Sanjeet Dwivedi, sir.
Thank you very much, Professor Chauhan, for introducing Mr. Mangesh.
thanks, Mr. Sanjeev. Glad to get your introduction. So we will certainly interact later on.
Sure.
Thanks
We will.
for you.
So, Dr. Sanjeet Dwivedi, he is at present with the Danfoss Drives. It is actually Danfoss Intelligence at Danfoss Power Electronics, and he is having a lot of I can say credentials to his I can say cap, many feathers. I'll just discuss a few of them. He is a project management professional, PMI of USA, and certified Scrum Master, trained Agile Project Manager, and he is having innovation and business skills. He has done Masters in Innovation and Skills from MIT, and I have this thing to say proudly that I was his junior to IIT Delhi when I joined PhD, and he was just about to leave his PhD program because he has completed that, and that association is still continuing, and I feel a kind of big brother feeling from Dwivedi sir always, and he has given all kinds of love as a youngster to me, and really it's always amazing to have him either online or personally. He is a graduate from MP, and he is a postgraduate from IIT Roorkee, and he has a lot of experience. He is working in Danfoss Drive since almost 11 years. So we have a lot of things to discuss with him, and he will be definitely putting all those things to this presentation, and participants, please get benefited from his experience. He has displayed all his credentials on the screen, so you can just go through that, and we are really proud to have him with us. So sir, please take over the dais.
Thank you very much, Professor Chauhan. And I will mention here specifically my email address is here. So if you are able to interact after the presentation, that will be nice. Otherwise, I will be very welcome to participant. They can contact me at a later time. So after this very, I would say thanks for this nice presentation. And this is my workplace where I'm working. This summer capital of Denmark, Gråsten. You can see this. Our office is in this area, backside of this. And this is our headquarter in Nordborg. That is the global headquarter of Danfoss. This is the 11-story building here in center part of here, and you see the this. Whole factory area. So we are, as you know, Danfoss is working for climate friendly solutions. So heating section, air conditioning section, and variable frequency drive section. So all heating, air conditioning, and power solution, they are here. And this is our solar plant, which is generating all the energy required for Danfoss. So as this presentation is on drive and drive application for EV and special focus on PM motors. So I will start with this punchline of our Danfoss drive, we are 100% focused on developing, manufacturing, and supplying AC drive. We are the world leader and first mover in variable speed control of electrical motors. Way before ABB and Siemens, we have invented this variable frequency drive control. Since 1968, that is our, we are in business and that is our focus. And in 2014, there were another milestone comes in the history of Danfoss drive. Danfoss and Vacan, they both merge and then form one of the largest company in the industry. And together, we will continue to driven by a passion to develop, manufacture, and provide the most versatile variable frequency drive. And our capability start from 180 watt to 5.3 megawatt. These are some of the Danfoss drive business area. You can see that digitalization, electrification, urbanization, climate change, and food supply. Here I will mention these. Specifically, I will mention about the electrification. So there are more than 20 million electrical vehicles. They are drive by our power module. So we are producing silicon carbide power module and a variety of other IGBTs, and they are extensively used in the EV industry. And our plant is located in Germany, 17 kilometers from Denmark. This place name is Flensburg, and another plant is in Iowa State in US. And in digitalization also we are doing a lot, and we are providing our customer a capability that they can diagnose not only their drive, motor and application, but they know their system, process and all those. And for that, we are providing all kind of support. So they can log in data in cloud and they can analyze those things. And we also provide services for that. And as you know, urbanization, so we are producing heavy electrical vehicle for agriculture industry. And earlier they were driven by hydraulic system, but now they are electrical. And in food supply, we are providing these big stores with all air conditioning and HVAC solution and all processing capability, so that this food waste in the supply chain can be reduced. An outline of my presentation is, I will give you a brief introduction of EV, and then I will talk about common technology. Then we will go through technology trend in EV. So you can see that not only PM motors, but you see what are the focus area of EV technology and where the research is going on worldwide and what are the interesting topics. And then I will come to the main focus of this presentation, drivetrain and introduction to electrical drive. We will talk about control technique for PMSM in EV application. And then I will give you time for question and comment. So this is the first electrical vehicle, and that was in 1891. So you see that how many years, 130 years ago, we were having a practical or a feasible solution. But you know, what were the reason why it was not get successful? Because of the oil lobby. And at that time, these oil explorative company and big giant, they think that they can earn a lot of money by selling oil. So this early innovative idea, which was a very, very nice idea to, if it was implemented, it was a game changer, and we were not face these climate change problem and all those things what we are talking about. This CO2 emission and all those things. But because of the oil lobby pressure, this idea was killed, and we have to wait for 100 years for that. This was in Des Moines. He invented with Morrison in Iowa State. So what are the present status of EVs? These are the company like Ford, Honda, Mercedes, Chevrolet, BMW, Nissan, Toyota, and Tesla. And They are noteworthy. Tesla is the noteworthy, and there are speculation nowadays that I heard last week that Tesla is serious to bring his plant from China to India. So that might be a good news. So this one is the Toyota plug-in Prius, and this is a plug-in hybrid electrical vehicle. Then another one is Chevrolet Volt. You see this again plug-in hybrid electrical vehicle. I will tell this. I will explain you the basic definition soon. Then this is the Ford C-Max Energy, and its range is very small, 21 miles. Then this is the battery electrical vehicle, Nissan Leaf. I will talk about drivetrain for this model, and I will give you a little more insight in the motor design and its performance, and that research is based on ORNL, Oak Ridge National Laboratory. So we will have some practical data, why the PM motor is used and what is its performance there. Then this is the Toyota RAV4 EV, 103 mile average electric range. And this is the famous Model S of Tesla, 260 mile and 85 kilowatt hour battery. And it is battery electrical vehicle. So how can we differentiate them? That's a basic definition. So if it automatically start the engine in stop and go traffic, it is micro hybrid, and Citroen C3 is example. If it is using regenerative braking and operate above 60 volt, then it is mild hybrid, and Honda Inside, that is the example. And if it is having all these three capability and fourth one can drive at time using only the electric motor, then that is the full hybrid. And if it's a recharge battery from a wall outlet for extended all electric range, then it is plug-in hybrid. So Savvy Volt, that is the example. We can have another outlook of these different technologies. So hybrid electrical vehicle powered by engine and electrical motor. That's why it is hybrid of these two. An internal combustion engine uses alternative or conventional fuel. So it can be a ethanol, or it can be a hydrogen. Just to mention here, there is a big boom in hydrogen energy. And if you look on the perspective of company like Neil Hydrogen or Everfuel or Tesla, even they are now Tesla is also investing on hydrogen fuel. So that might be a future for green energy. So additional to EV, we are talking about hydrogen energy too. And in Germany, you might know that there are certain trains, they are driven by only by hydrogen. So that's already in practical implementation. Fuel efficient system design, then mild hybrid cannot power the vehicle using the electrical motor alone, and full hybrid, more powerful electrical motor and larger battery, they can drive the vehicle. So then comes plug-in. So plug-in means you are having this possibility of fuel, conventional fuel, and then you can provide the electrical input in the battery to store the energy. So they are having both possibility. Internal combustion engine uses alternative or conventional fuel as well as battery charged by outside electrical power. This again having parallel plug-in hybrid vehicle or series plug-in hybrid electrical vehicle. In parallel, you are having engine and electrical motor. They both coupled to the wheel, and in series that engine is only used to generate electrical power, and motors and then this wheels are coupled with the motor. So these are two variant in plug-in hybrid electrical vehicle. Then comes all electrical vehicle. There is only possibility of electrical input, and battery size is bigger, and it driven by battery and motor, and then this topology is used by the Tesla. So battery store electrical energy that power the motor, and battery charged by plugging into outside electrical power source. So zero tailpipe emission, that is the advantage. And but as you know, air pollution may be produced through electricity generation. So in order to produce the electricity, you have to use some conventional energy sources, and that's why hydrogen is scientist and environmentalist thinks that hydrogen may be future to the EV. Driving range is 100 to 220 mile, and it is there are more addition on it with the new technologies. And there is a survey and a well-known conclusion that 100 mile is sufficient from more than 19% of all US household, and that's true for most of the people in India if they are not driving and they are not commuting from one city to another city. So this diagram is showing simple working, and you can see that how electrical vehicle and plug-in hybrid electrical vehicle are connected. You see here it's only the motor and battery in electrical vehicle, and here you are having combustion engine, and that is connected with the gasoline supply, and battery connected to the motor, and they both are driving wheel, so motor and combustion engine. So this is the from previous topology, it's a parallel plug-in hybrid vehicle, and you can see it's in the black diagram. It's simply explained how it's working. So if you replace small battery with additional battery, then you can increase the range of this vehicle. And if you add this electrical outlet, and then you can further increase the capacity. So they started with 20 mile range, then reached to 40, and then now we are talking about 100 mile range. So, and this is again the breakup of that survey, that 50% of all daily drive less than 25 mile, and average daily driving mile are 33 mile. Okay. So now comes to another important component of EV, that is the battery. What are the different type of battery use? So they start from lithium ion. It is still a popular candidate. Then research is going on nickel metal hydride batteries, lead acid batteries. There are some new discoveries on that, and people are thinking how this cost-effective solution can be reused, but it's still bulky size is a constraint. And then lithium polymer battery. This is also a good candidate. And this ultra capacitor, you already heard about ABB, this EV bus fleet in Geneva. So ABB is providing electrical buses for city transportation, and these buses are having a special capability. They don't need any charging. So that is a myth. This is not true, because they are using the battery as well as they are using the ultra capacitor. So in the night when they stop their operation, they charge their battery fully, but in the daytime when they stop in the stops, city stop, at that time they are using for a minute or two, they are using this ultra capacitor charging. So passenger cannot feel any interruption in the services, and operation is continuing. So additional to battery, they are also using the ultra capacitor, and that's also a kind of solution which gaining momentum for public transport. Then this battery recycle market, and this is going to expand very soon. And you might know that already Mahindra and Mahindra in India, they are investing a lot, and Tata is also investing a lot in India in the battery market. So there are some movement in India too. And then this battery swapping option, they are already there, but in order to get popular it's the same story like when we were witnessing our previous decades, that this drinking water, we never thought that there will be a swapping option for drinking water, that somebody will come and replace it. The same people thinking of that car battery is also a swapping option. So you go to the particular outlet and thus you replace your battery, or a battery replacing service come to your home. So you need not to charge by yourself. It is charged somewhere else and it's supplied to you. The only problem is how can we make secure movement, and how can we put this battery in the car and then take it out and follow all the security and these norms and standards. So, but it is the future. We'll see in future more and more this type of service. So, out of these all candidates, why all electrical vehicle is the most important one? The first one is the fuel economy. It don't use any liquid fuel. It don't have any tailpipe emission, and fuel cost saving, that is one, and the energy security. So that is another one. It reduces reliance on the imported petroleum, and the fueling flexibility. So can charge at home or public charging station. But the consideration is purchase cost. I will talk about it. There are global trend in the R&D, how these purchase cost is change, and when it will come to the in comparison to conventional car, when it will be to that range. But that can be offset by the fuel saving, tax credit, and the government incentives. Then public charging. Then infrastructure is in development still, although there are good development in our metros in India, but still for small cities it's needed time. And then this battery recycling and reusability, that is also needed special focus. And these are the charging system that there are different label and different technique. So level 1 is 120 volt alternating current plug dedicated circuit. Second, level 2 is 240 volt AC plug and uses the same connector on the vehicle as level 1. But then level 3, that is in development, faster AC charging. And a lot of work is going on the charger, and India is also playing a big role on this. So, and DC fast charging, that is with 480 volt and 50 kilowatt battery can charge in less than 30 minutes with this technique. And last but not the least, inductive charging, where there is no physical contact is needed between battery and the supply outlet. This due to the inductive charging, vehicle can battery can be charged with this special circuit. So if we compare our conventional gasoline-based car and electrical vehicle, what is the well-to-wheel efficiency? So if you look on electrical vehicle, you will find that generation losses 33%, transmission losses are 94%. So total losses in generation and transmission is 31%. And plug to wheel, that is the efficiency of electrical system, that is assume 76%. So total efficiency is 23% in case of electrical vehicle. But if you talk about gasoline base, then you see the refining and refineries which change which give you the required liquid form diesel or petrol, and it lasts 82%, and transmission 98% efficiency. So total efficiency is 80%, refining lasts 18%, and transmission lasts 2%. Then pump to wheel is 16%. So you see that only 13% is efficiency. If you are using the same fuel, even we are talking about worst case scenario, this is the diesel base station, but it can be a renewable energy source, or it can be a green energy solution like hydral, or it can be solar, or it can be wind, and that is having another numbers, and this efficiency is more than that. So you see just a ratio of 1 to 2 if you are talking about our conventional way to use electrical vehicle or with this electrical vehicle. These are some EV research focus area. And the most important one is traction drive system. So when we talk about traction drive system, innovative system design. And when it's innovative, it means modular and integrated solution to meet size, weight, and cost. This is the research report which I was talking about this year and 5 years back, 2 benchmark. And when it means an integrated solution, it means that in the existing frame, we need to provide our solution. So if you look in this diagram, you see that this is the conventional flange of internal combustion engine. But the inside, you see, your inverter is in circular geometry here. So this is your inverter, this part. This is your stator, and this one is your rotor, and then this one is your gearbox. So the same unit. So outside you don't see any difference, but inside combustion engine is replaced by the inverter and the motor. And this is the layout of integrated motor and inverter concept. I will talk about more in the next few slides. So, and this benchmarking is vital to program planning and project performance activities. So this, when we are talking about this model, this is the replacement of existing IC based this whole unit by inverter and motor. So being said that, you see these are the other focus areas. So new topologies for inverter and converter. This is a specific requirement that decrease in size and cost and improve reliability. So avenue to, if we achieve this, what are the benefit? Avenue to achieve significant reduction in P weight, volume, and cost, and improve performance. Reduce capacitance need by 50% to 90%. So yielding inverter volume reduction to 20 to 35% of cost reduction. Capacitor is the major part, DC link capacitor. If we can reduce that we can achieve it. And reduce part count by integrating functionality, thus reducing inverter size and cost and increasing reliability. So when we are talking about integrating functionality, then it means gate driver and production circuit and Cinnabar circuit. How can we have optimum design of our PCBs and how we place them so that we are having reduction in part count. And then reduce inductance, minimize electromagnetic interference, EMI and ripple. So we need to have innovative design as well as we must have EMI filters, and reduce current through switches, and all result in reduce cost. So we will get the improved performance, minimization in EMI, and by that we get better performance. Then this temperature tolerant devices. So I already mentioned that It is a standard in EV industry that we are not using silicon IGBT, silicon-based IGBT. We are using silicon carbide, which is wide band gap, and even there are new trend to use gallium nitride based devices. They produce higher reliability, higher efficiency, and enable high temperature operation. Then comes packaging, and we need a special packaging for EVs. So they greatly reduce power electronic size, cost, and weight with higher reliability. So this packaging provide opportunity for greatly decreased size and cost. Module packaging can reduce inverter size by 50% and cost by 40%, and enable a silicon device to be used with high temperature coolant. So either you use silicon device with high temperature coolant and cost saving by 25%, or enable use of air cooling. That is also possible by a special fins design of heat sink. And then device packaging to reduce stray inductance, improve reliability, and enable module packaging options. Then comes to the capacitor. As I told, this is the one of the major component which is having influence on overall size and weight of inverter. So there is, if we reduce 25% inverter size and it by 10%, so improved performance can reduce capacitor size by 20%, reducing inverter size by 10%. So if we reduce 25% capacitance, then we can reduce inverter size by 10%, and it also result in increased temperature limit. Then comes to the vehicle charging, and we can emphasize this area, and this area is also having a lot of opportunities. You see the inverter topology. It's a current source inverter is also a candidate for future research, and this is what the chip size, integrated chip size is used for reducing the part count, and these are the comparison of wide band gap semiconductors you can see in this slide. Then there are further areas, high performance permanent magnet motors. So cost is major concern for interior permanent magnet motor because of the rare earth magnet. Cost reduction to 75% are required to meet this target. Work on all aspect of motor design may reduce cost by 25% to 40%. You know, this is a very unpredictable component. This IPM motor cost is primarily depending on the rare earth element, and that element is imported. Everybody is importing it from China, and that is having a high degree of variability, and its cost fluctuate between 500%, and nobody can make sure that they will have secure supply. So trends change, and people are again like Tesla, they are not using PM motors. But as I told, Nissan Leaf, they are using it, and I will show why in next few slides. Then this magnetic material, as I told, for PM motor, magnetic material costs are 50% to 75% of motor, and this is area where we can think of how either to find a cheap magnetic material with all those required quality like high temperature and high energy density, or we can replace it by other technologies. And non-PM motor, they are also a good candidate for EV focused research. And new material like in lamination, as well as new technology to build the motor, like concentrated winding motor, they are also a good candidate. You can see here, this is the 16,000 RPM brushless field excited IPM motor, and these are the winding arrangement, and you see the magnet and the rotor assembly. These are some more focus area, that thermal system integration and then heat transfer technologies, and thermal stress and reliability. And I will not go through in detail because of the time constraint. Okay. Let's jump to next slide. So as we gone through previous few slides where we talk about, so most important one is the inverter topology to reduce cost and volume and to reduce capacitor requirement and having integrated functionality. Then packaging, then motor research, so reducing costs and addressing rare earth material volatility. Then advanced magnet material, non-permanent magnet motor concept, and in the end, thermal management technology to reduce volume and cost and enhance thermal reliability. So, what are the companies who are working for these research focus and research challenges? So they start from REMI, that's hybrid electrical motor and control, General Motors. They are also working on it. Ford Motor, Magna e-car system, Delphi automotive system. They are also working on this area. Ellison Transmission, UQM Technologies. They are also working on it. KMAT Corporation. They specifically working on DC bus capacitors. SBE and PowerX. So this is a consortium which is working in US, working on a specific project to research focus on the EV, the specific component of EV. This diagram is showing different component of electrical motor drive selections for EV. You can see here that this one is your motor here, and you see your IC is here. You see inverter is here, controller is here, your battery is here, and differential gear is here. So this is the layout of EV. Being said that, what are the requirements of motor drive for EV? It must have high instant power and high power density. It must have high torque at low speed for starting and climbing, as well as high power at high speed for cruising. Very wide speed range, including constant torque and constant power region. Fast torque response. High efficiency over wide speed and torque range, and it's quite natural, isn't it? If we are not having an efficient system, then our energy will be waste, and we will not get an opportunity to range. So not only we will invent high power capacity or high recharging range of battery, but we must make our motor and inverter as efficient as possible, so use judiciously the available energy. And high efficiency for regenerative braking. So when we are braking the vehicle, then we must reutilize that energy to charge the battery. And then high reliability and robustness for various vehicle operation conditions. So as you know, with the different grade of roads and different robustness requirement, we must develop our drive control algorithm which are not sensitive to these conditions. For example, if our position or speed sensor is not robust enough and our algorithm highly dependent on it, then there is a small component of few dollars can break the whole system, and then that must be robust, and we must have redundancy in our algorithm to diagnose this solution, diagnose this problem and provide a solution. So we get the redundant signal. So with the, that may be a downside, that we get very high, very highly accurate signal from the sensor, but with the estimation algorithm, we get the little less accurate signal, or this precision will be less. But we need redundant signal, otherwise, because of the road condition or operating condition, this sensor, a small sensor, that can ruin the whole system. So specifically, this point is mentioned here. And then, of course, reasonable cost. If you need any product, viable product, then you must have reasonable cost. And unfortunately, EV is still in the infancy mode, and cost is not to that level where it should be. But trend showing that soon, in a couple of years, it will be cheaper than conventional car. This is a overview of which motor drive is adopted by which EV industry. So you see that Peugeot is using DC motor. This Holden is using switch reluctance motor. Nissan is using permanent magnet synchronous motor. Honda, that they are also using PMSM. Toyota, they are using PMSM again. Renault, this is using induction motor. Chevrolet, they are also using induction motor. Daimler, they are using induction motor. And BMW, they are also using induction motor. Tesla is not here, but I already mentioned that Tesla is also using induction motor. But please keep in mind that when I'm talking about here induction motor, then this induction motor is, this is the rotor is made of copper. So it's not a conventional induction motor. It's a special induction motor which is having lowest losses. And for that, all these EV industries, they are using motor which rotor is built of copper. So as I told you earlier, this cost analysis and trained in electrical drive, trained in use in electrical vehicle, how is the train going on? So you see here for Nissan Leaf, all electrical vehicle, traction motor as the baseline comparator. You can see here the traction drive system and power electronic system, how's the cost is going on. So year is 10, 15, 2020, 25, 2030. If you see that power electronics cost, no doubt it will be drastically reducing. There are more and more manufacturers, there are more and more efficient processes, there are more and more topologies and new control algorithm that will making not only technologically advances, but scalability also in power electronic solution. So that cost is going down. And this electromechanical cost, that is also reducing. And then if you see that traction drive system cost, so based on these two cost train, it is reducing. And then if you see this cost analysis, that already this inflection point is reached in 2020, and it will be further and further reduced by coming year. So for sure, by next 5 years, this gap will be very less. Another thing, if you look in the train in traction motor speed, that is also going up and up and up. So by 2020, it already reaches more than 20,000 RPM. So invariably, this EV industry is using electrical drivetrain with more than 20,000 RPM speed. So, and this speed lies, this high speed, because this high speed result in the higher efficiency, and it's providing the benefit in terms of overall technology implementation. And then another one, this comparison showing us PM motor is used, but all the drive industry, all the EV companies, they are not looking to invariably looking for this PM motor, PM solution, PM rotor solution. And because I told you earlier, this rare earth magnet, neodymium iron boron, which is the backbone of PM motor, IPM or PMSM, that motor based on these magnets, they are designed for higher speed and using optimized rare earth content at 77. This is a comparison number by over Oak Ridge National Laboratory, $77 per kg, to show potential benefit of higher speed are lost when rare earth content dominate motor cost. You see here, this is the traction motor specific cost range. Goal is this, but still we are far away from goal. So conclusion is, charting the cost of IPM traction motor with speed 5,000 RPM to 23,000 RPM shows that an inflection point has already been crossed, at which point the historical learning curve transitioned to a shallow slope. This is a shallow slope, and by 2020 target $4.7 per kilowatt can no longer be achieved when RE is involved. So world need to look beyond RE, rare earth magnet, and that is only viable solution. Because you know that RE, rare earth magnet, they are not found in bulk. They are a processing and manpower, that is the biggest requirement to produce rare earth magnet, and China is having domination on that because of the cheap labor, and they develop a ecosystem which is controlling the cost of this. So although my presentation is focused on the PM motor, but keep in mind that we need to, this is at present it is one of the available solution, but when we talk about the cost benefit ratio and the viable cost of the EV, then we need to think of beyond this magnet solution. So these are the identified candidates for motor technologies. You see that baseline is interior PMSM, and then induction motor, switch reluctance motor, and synchronous reluctance or PM assisted synchronous reluctance motor. So this interior PMSM that developed in 1986, quite a new discovery. Induction motor invented by Tesla in 1889. Switch reluctance motor also quite old, 1900, and synchronous reluctance or PM assisted, that is 1923. This is electromagnetic torque equation. This is the well-known equation based on DQ model, which use the magnet flux and DQ axis inductance and DQ axis current for PMSM. Then for induction motor, magnetizing inductance and rotor self inductance and DQ axis current. And for switch reluctance motor, that is rate of change of inductance and current. And then for synchronous reluctance motor, that is based on inductance and current in DQ model. Power factor, it is 10:1 for IPM, less than 1, of course, for induction motor, and very poor for switch reluctance motor. And based on the this DQ axis inductance ratio and factor, depending on that, so how much difference is there in DQ axis inductance, how much saliency is there, that determine the power factor. So if saliency is more, power factor is more. And when we talk about suitability for high speed, Then this switch reactance motor is the best candidate. Second best is induction motor, and IPM and synchronous reactance motor. They are having the least performance on high speed. Efficiency, you see, quite natural, because in the IPM we are not only suppressing rotor losses, but also we are providing energy from the rotor side. So it's having highest efficiency. Then all three, all other candidate, they are having lowest compared to this. And cost for induction motor, that is plus, because its cost is less. Switch reactance motor cost is less, and synchronous electron motor little costly, but this PM motor IPM is the most costly one. So based on this analysis, why PMSM drive for EVs? Overall weight and volume significantly reduced for given output power. High power density, that is the one of key advantage of PMSM. High efficiency, as mentioned in previous slide. Heat efficiency dissipated to surrounding. So heat efficiently dissipated to surrounding, then this thermal model, that is, which is vital, because there is one assembly where integrated assembly where inverter and motor, they both place inside, and this cooling requirement, that is at most important in EV. So this is also one of the advantage. This is again Nissan Leaf interior permanent motor with rare earth magnet, and then comparison of high speed induction motor to commercial all electrical vehicle motor. So you can see here comparison of all electrical vehicle. You see data for this PM motor and high speed induction motor. So maximum speed, you see 10,300 compared to 23,000, and this dimension you see 151.3 mm, and this is 106.8. So all rotor outer diameter 130 mm compared to 1887.2. But you see rotor mass, then again 16.432 kg, and it is 5.602 kg for induction motor. Rotor inertia, this is again higher. Gear ratio for inertia balance, that is 1, and it is 2.55. Gear ratio for NMAX, that is 1.16 and 1.92. And shaft diameter is 44.45 and 34. So you see the most of the number, they are not advocating for PM motor. But as you know that efficiency for IPM, that is higher, and that lead to still a point for further investigation and use. And that's why Nissan Leaf is using it. This is 80 kilowatt IPM traction motor and water ethylene glycol WEG liquid cooled and 10,300 RPM motor. You see that this is assembly, and this one is your inverter assembly. This one is motor and integrated motor with all arrangement. And these are the comparison. Peak power, this is 55 kilowatt, and compared to Purus, that is 60 kilowatt. This is the Leaf, 80 kilowatt, and this is the Sonata. And these numbers, they are again, because my presentation is based on the report. So this was the research project, and they were talking about these target. And inverter, you see this specific power for inverter is 14.1 kilowatt per kg compared to Purus and Leaf and Sonata. And motor, you see that specific power 1.6 kilowatt per kg, and it's at par with 2010 previous model. Then power density, that is 5.7 kilowatt per liter. And these numbers are compared with all other model, and you see all the numbers are compared to previous model, they are higher. So it's a more efficient system. And system efficiency is greater than 94% compared to 93, 94, 95. These are some specific 10 kilowatt PMSM for Honda Insight, that is the model, and this is the 50 kilowatt PMSM for Toyota Prius. So you can see this assembly. This is your PMSM is integrated in this part, and the same PMSM is integrated in this part, and this is the assembly for PMSM. So being said about technology train, the research focus area, and how things are done for different electrical vehicle companies, now comes to the control technique for PMSM drive or for EV drivetrain. So there are basically there are two advanced control technique that they name direct torque control and vector control. There is third one, direct power control, and I will focus my presentation next slide, this slide onward, on vector control PMSM, because that is in principle used in EVs. So we will talk about design, modeling, and simulation of vector control PMSM drive. I will show some experimental investigation result, then some conclusion on it. Utilization of PMSM, as I earlier mentioned, high efficiency, high torque density, sensorless control, because PM motor is having a special advantage that its rotor is acting as a transducer. Because of the magnet, when PMSM rotate, this rotor induce voltage in the stator, and that voltage can be used to track the rotor position accurately. So sensorless control is easily possible in the PMSM or motor with the magnet. And another thing is there is no slip involved. So unlike in induction motor, because of involvement of slip, which is not a fixed number, that is varying with the environment, that is varying with the load, that is varying with the operating condition. So in PMSM, this is absent. So that is also sensorless control is more accurate. Lower cost, better reliability. And two main sensorless control method, back EMF based method and high frequency signal injection based method. So although magnet act as a transducer and it provide the rotor position, but for providing the rotor position, it need to rotate. So when it is not rotating, you don't get any positional information. For that, you need to use another technique, and that is you inject high frequency signal, and you analyze this high frequency signal response. So you inject voltage, and then in the result, what current flow through the motor, that current is analyzed for the positional information. So at standstill and low speed, until where you are having a significant amount of back EMF, we are using high frequency injection based method, and then afterward back EMF based method. So when we're talking about back EMF based sensorless control method, that is since the rotor north pole is fixed to rotor D axis, we define in the DQ axis frame, synchronous frame, that rotor north pole is fixed to rotor d-axis. And this rotor position can be obtained by the rotor flux location. So if we identify the back EMF and we integrate it, then we get rotor flux. And by knowing the vectorial position of rotor flux, we know that is the rotor d-axis position. And because there is no slippage involved, then alignment is always fixed with that. So there is no mismatch or no adjustment is needed, unlike induction motor. Limitation, as I told, stand still and low speed, it is not possible to get the positional information. And then there is some dependency on the motor parameter or machine parameter, because we are estimating back EMF, and for that we need to know accurately this stator leakage inductance as well as stator resistance, because they are having a role in estimating the back EMF. So if there is a variation in leakage inductance and variation in stator resistance, that will affect our accuracy of position estimation. And another issue is integration is involved in the calculation of rotor flux and the drift problem that is observed. So that is this DC drift in integration, that is the issue. Although there are some advanced algorithm which compensate it, but as a researcher, when we are implementing it and we are investing it, we need to pay special care for that. This is the block diagram of vector control scheme for PMSM. Here you can see that this is our motor, and this is your drivetrain, and this is your connected load. It can be EV or the wheels connected here with this shaft. Okay, and then you are sensing the current, two-phase current out of three-phase, and then the rotor position is also used here. It can be with the sensor based control, or if you are having mechanical sensorless control, then you can break this path. From here, you are providing this feedback current to the current controller. And from here, you see these are this is the reference speed. So reference speed and estimated or measured speed is fed to the speed controller. And estimated or measured speed is fed to the field weakening controller, because this speed will determine how much, what is the appropriate value of magnetizing current or d-axis current. So speed controller output and field weakening controller output, that will, and then this positional information, that will define the reference current. What is the current needed in the motor? And these reference current are compared with the actual measured current that will drive the inverter. So this current error is fed to the current controller, and current controller will give the specific pulses to 2 level 6-inch inverter, and it will drive the motor. So this is the scheme for vector control PMSM drive or field oriented control PMSM drive. This is the simulation model. You can see here, this is the PMSM, and this one is your inverter. This is vector controller. These are your position information converted to sine and cos for reference frame transformation, and these are the measurement block, provide the current, feedback current here, speed here, and position here. This one is the implementation of field oriented control PMSM drive. This is the black graph showing the implementation, and it is implemented with analog devices, motion control DSP 401, You see that internal part is speed controller, field weakening controller, position calculator, position to speed calculator, pendulum current controller. They are implemented in the mnemonics code inside the ADMC 401. And the pendulum pulses are coupled with the gate driver for IGBT, and this was a semicron inverter that was controlling the motor, and this is the resolver to digital converter is used to get the position, to get the positional and speed information. An advantage of RDC is that you get output which is sine and cos of rotor position, which can directly use for reference frame transformation and current controller when we need to current transformation and all those required mathematical operation. So this one is the basic PI controller. You can see the equation here. I don't think we should go and explain it, but this is the PI controller part, and this is the design of PI current controller. So you are having two current controller, one for Q axis current, one for D axis current. This is PI controller is implemented with the anti wind up, and then you are having this cross coupling term here. So in order to make it linear, these current controller, and remove the cross coupling term. So you are adding omega is ID to the Q axis, and you are subtracting omega is IQ to the D axis part. So you write the voltage equation now. These are our voltage equation for D axis and Q axis. ID is the D axis flux, IQ is the Q axis flux, RS is the stator resistance, and ISD, ISQ is D and Q axis current. So then you take in the S domain and you find these two equations, and based on these two equations you develop these transfer functions. So for D axis and Q axis you are having these two transfer functions, where TSD is the time constant for D axis component, and TSQ is time constant for Q axis. Then you model this Q axis and D axis in different block diagram. For Q axis, this is the PI part. This one is the delay for control algorithm, where TSW is the control task time. This is the delay for EDC, where TSW is the 0.5 TSW is the delay in measurement, and this is the delay in inverter. So you give the pulses, but the output is assumed that there is a delay of half of the switching period. So total delay is there is a 2 switching period delay here, and then inherent characteristics. So there is electrical time constant of the IPMSM. So that is their TSQ, and then there is a sampling delay in feedback circuit, that is the 0.5 of T switching. So based on this model, we can accumulate the delay, and these cascaded delays are added, and we can use the delay due to the sample and hold element, and it is introduced by a first order transfer function. And then delay introduced by the modulation technique and inverter. This delay is introduced by the again first order transfer function, that is a time constant equal to 0.5 of T switching. So if you solve these all those delays, you will get this transfer function, open loop transfer function for Q axis current controller. And if you solve it further, you will get the root loops plot, and you get a time constant, specific time constant based on the motor parameter, electrical parameter. Here, this one is the motor dependent, and this one is dependent on your control task time and your ADC and other delay in the inverter and measurement. And based on that, you get what is the PI controller gain. And that way, using the optimal modulus or your damping equal to 1 by root 2 optimal damping 0.707, you can use this optimal modulus criteria. And based on that, you will get the KPQ proportional and integral time constant. And this is the Bode plot for design PI controller for Q axis. And you see that there is a 13.6 degree, 13.6 dB gain margin and 62.5 degree phase margin in this design. This is the time step response, and you see the system is having a rise time of 1.8 millisecond and settling time of around 3.5 millisecond, and maximum overshoot is well within 5% band. So taking account this design, we will get this Q-axis current closed loop transfer function, and we get the time constant for Q-axis current controller. In similar way, we can design the D-axis also. This is another type of controller. This is sliding mode controller, which is based on the particular controller operate on the basis of switching function. So error and change of error, speed error and change of speed error, we use them. And we are using the hyperplane to determine the slope, and based on this change in error and rate of change of error, we will using these constants C2 and C3, and we define these values. So phase plane trajectory of sliding mode controller, you can see here. This is your this is the limit line, and this is your actual trajectory on the sliding line. That is, this is your sliding line C1, Y1, and plus Y2, where Y1 and Y2 are your error and change of error in either current or speed, wherever you are implementing this controller. And this is the simulation diagram for MATLAB-based simulation diagram, how it get implemented. Then this one is the fuzzy-based PI controller, and fuzzy logic is used for pre-compensation. I will not go in detail, but I can show that, and it was implemented for speed control. So for speed controller, we have taken the speed error and change of speed error, and we defined them in 7 membership functions. So negative big, negative medium, negative small, 0, positive small, positive medium, and positive big. And then we have used a center of gravity method for defuzzifying it. And this one is the fuzzy hybrid controller, where fuzzy logic controller and PI controller, they both use parallelly, and near to set point, PI controller take over control, and far away from set point, fuzzy logic controller will activate it. And the advantage of this approach is that the inherent chattering of fuzzy logic controller can be avoided. If we switch to near to set point, we switch to PI controller, and we are getting the optimal of fuzzy operation and PI operation. So you see here, this is you can maybe just omit this part because it's a both directions, so you can only see if the positive direction for simplicity. This is your set point. So as soon as you come to this region here, PI controller take over. But if you go away from here, so in the starting or speed change, or when you are away from the set point, then control is taken over by the fuzzy controller, and that is faster compared to PI controller. This was the hardware setup. You can see the ADMC401 here. These are the gate driver circuit. These are the isolator you see there here. And this one is auxiliary power supply. And these are the Hall effect current sensor used. This was the semi-current inverter you can see here. And this was the control board. And this was the motor. So one motor, they were connected mechanically. One motor is used as a test motor, and another one as a load drive. So another one is connected to the load. But you can see there are two cables, one for power and one for resolver. So in load motor, you don't need any resolver, so you are using only power cable here. These are the experimental result for PI speed controller. You can see that 251.32 radian second reference speed, and it reaches in around 1.14 second. And these are the phase B and phase C current. So left one is the simulation result and right one is the experimental result. This one is with the sliding mode speed controller, and this one is with the fuzzy PI speed controller. This one is the hybrid fuzzy PI controller. So going through our presentation, I would conclude here that different type of EV technologies are introduced, various electrical motor drive are presented, control method of PMSM drive is presented, and it is observed that market is adopting PM machine for EV due to their advantages, but care must be taken for the fluctuating price of rare earth element and rare earth magnet. So thank you for your patience, and now it's time for the question.
So dear participants, is there any question? I hope there is no question. And if there is any kind of question arises later on, you can mail to sir directly or to us also. We'll try to give
I'm
you
writing my email, and participant can write to me. I will be happy to give the answer. So just please introduce that you attended this MANIT seminar and you attended that, and then I will give you answer.
So thank you very much, sir, for your time. You have spared your valuable time, and we are really thankful to you. From all this ATAL FDP MANIT team, I express deep sense of gratitude to you for your valuable presentation and time. Thanks once again, and hopefully we'll continue on this kind of cooperation.
Thank you so much, Professor Chauhan, and I wish you all the success, and I hope our participant will be benefited, and if they need any help, I will be available. Thank you so much, and bye.
Thank you, sir. So participants, we close here the today's session, and we'll meet tomorrow